All right, this is modeling functions and applications. This will be a calculator-heavy section. So the idea of modeling, which is also called regression, is a major component of the AP Precalculus curriculum and will be revisited throughout the course. These topics will utilize the graphing calculators heavily and often include context. In Unit 1, we will work with regression models for polynomial functions, which are linear, quadratic, cubic, and quartic. That's fourth power. And for rational functions. So building regression models on the graphing calculator, a couple easy steps. First, you enter the data to be modeled. Second, you select the regression model. To enter the data, you'll press the Stat button on the TI-84 and then select Edit. Then you enter the data into lists L1 and L2. Then you go into the Stat menu. You go over to the Calc menu, which is the second one over here, and you'll choose the model you want. Notice there are two linear regression options, option 4 and option 8. They're basically the same. If you're in AP Stats, you would want to use option 8. We'll probably use option 4 more though. Just be careful about where the A and the B are in those. In option 4, it's AX plus B. In option 8, it's A plus BX. Just changes what numbers they're going to list as A and B. You'll enter L1 for X list and L2 for Y list. L1 and L2 are in blue above the 1 and 2 buttons. You just press second and then those. And a tip to store the equation, enter Y1. So if you press alpha and then trace to pick Y1, it'll save your equation in Y1 and make it easier for you. So let's look at an example. The age in weeks and weight in kilograms of 5 randomly selected babies from a particular pediatrician's office are listed in this table. A linear regression, y equals a plus bx, can be used to model these data, where y is the predicted weight of a baby in kilograms that is x weeks old. Let's write the equation of the linear model for this data. So I grab my calculator. I press Stat, and then I choose Edit. Now I clear out my list, so if I go up to L2 and clear, it'll clear everything. All right, do the same thing for L1, clear everything. In L1, I'm going to enter my t values. So I'll have 4, enter, 5, enter, 6, 8, 12. Go over to L2 and I'll enter my weights. So 4.2, 4.4, 4.8, 5.1, and 5.7. There we go. I want the linear regression model. So now I hit Stat and I go to Calc. I want linear regression, but it says A plus BX. So I actually want to go to option 8. Notice it automatically populates us with L1 and L2. That's what I want. Skip frequency list. Notice store reg equal, right? If you hit alpha, trace, and choose Y1, that way it'll store it for you. Then I go down to calculate and press enter. And there it goes. It tells me A plus BX, so A is 3.545, B is 0.185. So that means my linear regression model is Y equals 3.545x plus 0.185. It's helpful to store these values in a Y equation because otherwise sometimes they're really long decimals and you are inclined to round them. So using our model, let's find the predicted weight of a baby that is 10 weeks old. Here's a tip. You can quickly find values that are saved in Y1 by doing this. Clear out, hit alpha trace, and choose Y1. Then in parentheses, just like function notation, enter the value I want to put in for x, which is 10. Press enter and it's 5.395 kilograms. And now the weight of a 6th baby is 5.3. Using the model from part A, what is the age in weeks of this baby? So I know y is 5.3 equals 3.545x. Ooh, what did I do? I put my x in the wrong place this whole time. I apologize. My x didn't go there. My x went here. That doesn't affect my second answer, though, because I had my equation stored and I didn't have to type it in again. So my mistake actually wouldn't lose me double points. But make sure my x goes here because that's what my regression equation said. So it's not no x there. It's plus 0.185x. Now we just solve. Subtract the 3.545. I get 1.755 equals 0.185x. Divide by 0.185. I get 9.486, oop, you can't see that, sorry, weeks. Always round to at least 3 decimal places. All right, so then we're going to talk about something called residuals. When we use a model to predict values, we expect our model to produce values that are reasonably close to the actual values. But our models are not expected to result in exact values generally. The difference between an actual value and the value predicted by a model is called a residual. So a residual is the actual value minus the predicted value. So using the model we found in example 1, let's find the residual of a baby that is 5 weeks old. So the actual value is what it gave me in the table, 5 weeks old. That baby was 4.4 pounds. The predicted, I take my calculator and I choose Y1 again because my function is still stored. And I plug in 5 weeks, I got 4.47. So my residual is actual minus predicted, which is negative 0.07. So the interpretation is that the actual baby weighed 0.07 kilograms less than predicted. All right, using our example found in example 1, our model, a baby that is 7.5 weeks old had a residual of negative 0.7. What was the actual weight of the 7.5 pound or week old baby? So actual minus estimated equals residual, which is negative 0.7. Well, the estimated we can find using 7.5. Plug into my calculator here. Oops. Y1 of 7.5. My estimated is 4.9325. So something minus 4.9325 equals negative 0.7. Add the 4.9325. I get x equals 4.2325 kilograms. That baby actually weighed 4.2325. Now we're going to sketch the residual plot for the 5 data points in the table. And to do this, I want to take my table and I say, all right, 4 weeks. Let's see what my prediction is for 4 weeks. It's 4.285. The actual was 4.2. I subtract 4.285. Oops. There we go. I get negative 0.085. So let's see what all my values are first. All right, so at 4 weeks, my residual is negative 0.085. 5 weeks, let's see here. 4.4 minus my predicted value at 5 weeks is negative 0.07. We already figured that out, didn't we? 6 weeks, take my actual minus my predicted at 6 weeks. I get positive 0.145. Oops, 8 weeks. Take my actual minus my predicted at 8 weeks. I get 0.075. And at 12 weeks, my actual minus my predicted 12. So I see that my biggest value is 0.145. So I'm going to go 0.05, 0.1, 0.15. And negative 0.05, 0.1, and negative 0.15. So I'll plot these at 1, 2, 3, 4, negative 0.085, right about there. At 5, I have negative 0.707, sorry. At 6, I have positive 0.145. 8, I have positive 0.075. oops, I go off my graph a little bit. I have negative 0.065. There's the graph of my residuals. You can also make residual plots on the calculator. So to make a residual plot, you must have already entered the data and calculated the regression model. You'll need to press second and then y equals to open up the stat plot menu. All right, so second, y equals, we'll open up stat plot. You'll choose plot off, first plot, one plot off, and then you'll turn the plot on and select the plot type. You can use a scatter plot, a line graph, bar graph, all sorts of different plots. We need to choose the X list, L1, and Y list, resid. So you have to change it to resid. So you have to change it from L2 to resid. And notice it gives you options. And then you'll graph the residual plot and hit zoom 9 for zoom stat. And that's what our residual plot should look like. So let's find out. I hit second, stat plot. I choose number 1. I turn it on. X list is L1. Y list, though, I want to delete that. And I want to choose second, stat, 7. Second, stat, 7. Resid. I can choose my marks. I can choose my color. I hit graph. And I got some weird stuff going on. That's my line of prediction. I don't care what it actually looks like. If I hit zoom 9, it zooms in on my residual plot. So here we have a table that has data for 8 ordered pairs. We have to decide what function type would best model the data, linear, quadratic, cubic, or rational. And we can choose that using characteristics of the data in the table. And then we'll write our regression model. So one characteristic to look at is called the differences. So if I look at the first differences, I take my table and I'll extend it up here. You probably want to extend it down, but I look for the difference between these two. There won't be a first difference in the first spot, but 10.6 minus 5 is 5.6. Then 15.4 minus 10.6 is 4.8. And then 17.1 minus 15.4 is 1.7. 18 minus 17.1 is 0.9. 16.5 minus 18 is negative 1.5. 10.2 minus 16.5 is negative 6.3. And 2.8 minus 10.2 is negative 7.4. If those first differences were all the same or very close to the same, that would be good for a linear model. They're not all close to the same. So I'll check the second differences. For second differences, I subtract the first differences from each other. And that would be for a quadratic. So there won't be a second difference in the second box or the first. 4.8 minus 5.6 is negative 0.8. 1.7 minus 4.8 is negative 3.1. 0.9 minus 1.7, negative 0.8. Negative 1.5 minus 0.9, negative 2.4. Negative 6.3 minus negative 1.5 is negative 4.8. Negative 7.4 minus negative 6.3 is negative 1.1. Those second differences also were not the same. Let's check third differences. That would be checking for a cubic function to fit. We won't have a first, second, or third difference here. Let's take negative 3.1 minus negative 0.8, negative 2.3. Negative 0.8 minus negative 3.1, positive 2.3. Negative 2.4 minus negative 0.8, negative 1.6. Negative 4.8 minus negative 2.4, negative 2.4. Negative 1.1 minus negative 4.8 is 3.7. And I actually just did this whole problem making a big boo-boo. I assumed that all these x values were evenly spaced apart. And while most of them are pretty close, they aren't quite, which means my linear checking and my quadratic checking and my cubic checking are off. I apologize for that. You just watched me check all of these for nothing. We need to check the average rate of change. Instead of the first differences, we need average rate of change. AROC. So, instead, the average rate of change is 10.6 minus 5 over 4 minus 0. 4. That average rate of change is actually 14. Let's make myself a nice little table here. And then 15.4 minus 10.6 over 0.9 minus 0.4, which is 0.5. So that's 9.6. And then 17.1 minus 15.4 over 0.3, which is 5.7. I'm going to round there. And 18 minus 17.1 over 0.5, 1.8, and 16.5 minus 18 over 0.5, which is negative 3, and then 10.2 minus 16.5 over 0.7, which is negative 9, and then 2.8 minus 10.2 over 0.5. Notice that my average rates of change are going down, but they're kind of pretty darn close to symmetric on either side. Let's find our second differences now. Now that they're average rates of change, we should be okay. We won't have one here, but negative 4.4, negative 3.9, negative 3.9, negative 4.8, negative 6, negative 5.8. They get a little further apart, but the y values go up and then down. Well, what goes up and then down? A quadratic. And the average rate of change is pretty darn close to symmetric. So we're going to use a quadratic to model this, because the average rate of change is approximately symmetric, except positive then negative. So let's write an equation for our regression model. So we take our calculator, we hit stat, edit, clear out what we have in our list before, enter my x values, so 0, 0.4, 0.9, 1.2, 1.7, 2.2, 2.9, and 3.4. Then enter my y values, 5, 10.6, 15.4, 17.1, 18, 16.5, 10.2, 2.8. Stat calc, we want a quadratic regression. L1, L2, oops, I cleared that out. So I hit stat, oops, my goodness. I'm just clicking wrong things here. Stat, calc, quad, there we go. L1, L2, store it, let's store it as y1, and calculate. And now we have our answer. A, B, C, ax squared plus bx plus c. My equation is y equals negative 4.248 x squared plus 14.480 x plus 3.701. We always want to store it because this is definitely a bit rounded from what those actual numbers were. And one last example for us here. The table gives 7 ordered pairs. Using logarithmic regression, we're going to find a natural logarithmic function f for y as a function of x. Write an expression for f of x in the form a plus b ln of x, where a and b are constants. So we grab our calculator, go into our lists, clear out what we had before, and enter these values, 0.3, 1.6, 3.2, 4.7, 7.1, 8.8, and 10.3. And then 0.9, 3.3, 4.9, 5.7, 6.5, 7, and 7.1. I want to calculate my LN regression, natural logarithmic regression. List 1, list 2. Let's store it as y1 and calculate. Notice it says a plus b ln of x, and that's what I was looking for. So I've got my a and b values. So my equation will be f of x equals 2.864 plus 1.818 ln of x. The residual plot is given here. What are the coordinates of the point labeled R? Right here. Well, it's my second coordinate, so it must be 1.6 for my x value. And the residual value, remember, is actual. My actual was 3.3 minus my predicted. So that's f of 1.6. Let's see what f of 1.6 was. I take y1 of 1.6. It was 3.718. So I want to know what 3.3 minus that answer was. Oops. Answer. So this point was 1.6, negative 0.418-ish. Does the residual for the point R indicate that the model underestimates or overestimates the value of y at this value? Well, since it's negative, actual minus estimate is negative, so the estimate was bigger, so we overestimated. Because negative residual means predicted is greater than actual.